Okay, let's take a look at this problem. So we have a thermocouple here. We have a spherical thermocouple here. So we are interested in calculating time for this thermocouple to reach 115 degrees Celsius. Okay, 115 Celsius. This thermocouple is initially at T initial is 25 degrees Celsius. This is the initial temperature. And the temperature is changing due to the contact with a gas. So there is a gas flow here. So the temperature of this gas is 125 degrees Celsius. And the corresponding heat transfer coefficient is given to be 210 watt per meter square per Celsius. Okay, this is given to us. And we also know the heat capacity, which is 320, and we know the density, and we know the thermal conductivity of this thermocouple. So now the question is, how are we going to analyze this problem? So let's start with our assumptions. What are our assumptions? So we'll assume junction is perfectly spherical. Junction is perfectly spherical. So that means this pink connections are not important. Okay, that's first assumption. Assumption number 2, thermal properties are constant. Thermal properties are constant. So that means K rho Cp is not a function of temperature. Okay? Temperature or time. Okay? And finally, radiation effects are negligible. Radiation effects are negligible. Okay, these are 3 assumptions. So now, first, we need to see if we can use the lump capacitance method. So to check the lump capacitance method, I need to calculate the BO number. BO number is H times L sub C over K. So H is given. H is 210 watt meter square per Celsius. K is given, which is 35 watt meter per degree Celsius. So now LC, which is not known, which is we need to calculate. In this case, we have a sphere, and for a sphere we have LC, which is equal to LC, we have sphere, which is R0 over 3. So now let's use this information, LC, which is V over a surface, and which is R radius over 3 or diameter over 6. In this problem we are given diameter, so that means LC is diameter is 1 millimeter times 10 to the minus 3 divided by 6. So this is in meter, so we have 1.67 times 10 to the minus 4 meter. So now we have all the values that we need, so we can calculate the BO number. BO number is 210 multiplied by 1.67 times 10 to the minus 4 divided by 35. So we have about 0.001, and this is less than 0.1. So that means I can use the lump capacitance method. So the lump capacitance method is applicable. Okay, so now after I know this, after I know that I can treat this problem as a lump, so then the analysis becomes straightforward, because we only have convection now. So the gas here, if you go back here, so we only have convection due to that gas. So the analysis will be minus H times AS T minus T infinity rho V rho Cp, or let's just write it rho V Cp dt by d time. Okay, now let's rearrange this equation. So we can collect the temperature terms on one side. So we have T minus T infinity so we have minus H AS, this is constant, divided by rho V Cp times d time is equal to dt by T minus T infinity. So as we did in the previous case, you can call T minus T infinity as theta, dt as d theta. So that means minus H AS rho V Cp times dt is equal to d theta by theta. You integrate both sides, so you have minus H AS rho V Cp times T. The integration is from 0 to T, theta initial to theta. So we have ln theta over theta initial. And then if you want to calculate, if you want to pull out theta, we'll take the exponent of both sides. Exponent of the log is going to cancel, so we'll have theta by theta I is equal to exponential minus H AS over rho V Cp T. Or if you want to back substitute T instead of theta, we'll have T minus T infinity over Ti minus T infinity exponential minus H AS rho V Cp T. And we have our expression here. And what was our goal? Our goal is to find the time to reach a temperature of 115 degrees Celsius. So T to reach, time to reach 115 degrees Celsius. Okay? So now it is just a matter of substitution. We have 115 minus T infinity is the gas temperature, which is 125. T initial of the sphere tip is 25. T infinity is 125. Exponential. So we have H, which is 210 in metric unit. A surface area. The surface area of the sphere is pi, 4 pi r squared. And the density of the sphere is given, so which was a metal which was given in the problem. So let's go back here. So this was 8500 kilogram per meter cube, so rho is given, so which is 8500, and the volume of the sphere is 4 over 3 pi r cube. Cp is also given, so Cp is also given, and which is 320 times 320. T is only unknown, so And again, radius is given, so the diameter is given, we need to calculate radius. So the diameter is 1 millimeter, so that is 1 times 10 to the minus 3 meter. Radius is 0.5 times 10 to the minus 3 meter. So only unknown here is t. R is given, all others are numbers. We substitute, we calculate. So we'll have t is equal to, if you want to write one more step here, so this is going to be 10 over 100. 10 over 100, which is equal to 0.1, is equal to exponential some number times t. And if you carry out this, you'll find that t is equal to 4.98 seconds. Okay? So this is the analysis. In this case, in this problem, I started from the beginning. I derive all the steps. I derive my own expression for the lump capacitance method. And then I use the fact that I know the temperatures, what temperatures we need to reach, and then just substitute it. On theory, I mean, when you are solving this, after you get familiar with this topic, you can just go back the equations that we already derived, and you can start from there. You don't need to repeat the analysis again. If you start from this equation here, if you take a look at this equation, so we obtain exactly the same equation because the problem is exactly the same geometry. So we have only one term, and only term that we have is convection, and it is a convective heating or convective cooling. And in this case, we knew all the temperatures, initial, final temperature, and ambient temperature. Only unknown is T. This is how we calculate this problem.